Welcome to the first lesson in which we will discuss the half-life of a radionuclide. My name is Antonia Denkova, and in this module I'll teach you some basics that you will need to know to understand the following modules. You probably are not aware, but radioactivity is all around us. Only we cannot detect radioactivity with our eyes. For that we need special devices, like for instance a cloud chamber as shown here on the slide. In this cloud chamber you can visualize radiation which interacts with a supercondensed liquid and results in these very pretty tracks. If we're only looking at natural radiation, that is the radiation surrounding us, we will have just a few tracks, as you can see in this short movie. But what is actually radioactivity? Radioactivity is a spontaneous phenomenon in which a radioactive atom will emit particles or highly energetic electromagnetic radiation trying to get to a more favorable energetic state, so trying to get to a more stable state. We define radioactivity of any substances as the number of spontaneous nuclear decays, or also called transformations or disintegrations per second, as shown by this formula, in which A is the activity and N are the number of radioactive atoms and T is of course the time. If we have several different radioactive substances, we can simply add the activity of the different mixtures. The unit that is used to denote radioactivity is the becquerel, which is equal to 1 disintegration per second, or 1 decay per second. It is named after Henri Becquerel, who together with Marie and Pierre Curie discovered the phenomenon of radioactivity. Although becquerel is the SI unit, so the official unit, many people still use the Curie unit, especially in hospitals. As you can see, 1 Curie is equal to 3.7 times 10 to the power of 10 becquerel. Radioactivity is a spontaneous phenomenon, meaning we cannot predict when a radionuclide will decay. However, radioactivity is proportional to the so-called decay constant, lambda, times the number of atoms at a certain time. And this decay constant quantifies the probability the decay will occur. If we know the decay constant and activity, we can, for instance, determine the number of radioactive atoms in a sample, or vice versa. If we know the number of radioactive atoms, we can determine the activity of a sample. If we solve this differential equation, we will end up with an equation that we can use to determine the number of atoms at a certain time if we know the number of atoms at the reference point, the elapsed time, and the decay constant. Since the activity is related to the number of atoms, we can also convert this equation in a way that we can determine the activity at a certain time. For this, we must know the activity at the reference point, so for instance at time 0, the elapsed time, and the decay constant. Thus, activity is calculated the same way as the number of radioactive nuclei. But how can we determine the decay constant? The decay constant is related to the half-life of a radionuclide. That means the time that is needed to decrease the activity of a sample to half of the original activity. Here you can see a graphic representation of decay and the half-life, which is achieved when the activity has halved. You can see that 50% has been converted to another nuclide. The decay constant is related to the half-life according to the following equation, where ln2 is the natural logarithm of 2 divided by the half-life. Every radionuclide has its own half-life and therefore its own decay constant. In nuclear science, we use our own nomenclature to denote nuclides. For this purpose, we define the mass number A, which is the sum of protons and neutrons, and we place that on the upper left side of the nuclide in question. At the bottom left side, we write Z, which is equal to the number of protons. An example is, for instance, hydrogen-3, which has 2 neutrons and just 1 proton. So the mass number A is 3, shown on the upper left side, and Z is 1, shown on the bottom left side. When nuclides have the same number of protons but different number of neutrons, we call these nuclides isotopes of each other. The simplest examples are the isotopes of hydrogen, showing here 3 of them. Isotopes can be stable, meaning they will not decay, or unstable, meaning that they are radioactive and will decay with their own decay constant. Here, for instance, you can see that hydrogen 1 and 2 are stable, but hydrogen 3 is radioactive and has a half-life of 12.3 years. Let's now try to calculate the decay constant of hydrogen 3 if we know the half-life. We use the formula that links the half-life to the decay constant as discussed previously. Only we need now to convert the half-life of hydrogen-3 from years to seconds. That is needed since activity is given in disintegration per second, so in becquerel. To convert the half-life from years to seconds, we need to multiply it by the number of seconds in an hour, that is 3600, the hours in a day, that is 24 hours, and the number of days per year, that is 365. This results in 1.8 times 10 to the power of minus 19 per second. Now, can we calculate the activity of a sample that contains hydrogen-3, considering that we know the decay constant and that there are 1.2 times 10 to the power of 20 radioactive atoms? Yes, we can, by using the equation that we discussed previously. If we fill in the decay constant and the number of atoms, we get that the activity of this sample is 2.16 times 10 to the power of 11 becquerel. Finally, let's talk about the nuclide chart. The nuclide chart is a chart in which all known nuclides are placed, and that is very useful to find out the half-lives of radionuclides. This chart has on the x-axis the number of neutrons and the y-axis the number of protons. The nuclide chart is often used to determine the newly formed radionuclide after decay. I will show you some examples in the next lesson. Thank you for following this lesson. Next time we will discuss the different types of decay.